Okay, we've got ladders, and here it is, question number 1. So we've got a uniform ladder AB of mass 25 kilograms and length 6 meters, rests on rough horizontal ground. It's leaning against a smooth vertical wall. The coefficient of friction between the ladder and the ground is 0.25. The ladder is inclined at 60 degrees to the horizontal. And then we've got a man of mass 75 kilograms who's climbing up the ladder. And we've got to model the man as a particle and find out how far he can walk up the ladder before it starts to slip. So there we go. There's our question. Draw this out. A drawing is going to be super important. So make sure you get a good drawing out, have a go, and we'll catch up in a couple of seconds to go through the answer. Righto, it is solution time. So let's get cracking. Now we've got a ladder. It's resting on the ground on one side and against a wall on the other side. So let's start by making a drawing of that. So let's say this is the ground. Here's our wall, and then we've got our ladder. Let's do that in blue. Here we go. There is our ladder. So there it is. The ladder is 6 meters long, so I'm just going to put maybe 6 meters just here for now. We can change that about in a minute. And it's got a mass of 25 kilograms, and it's uniform as well. So uniform meaning that its weight or its mass acts directly at the center. So we can put that down there, and let's label this as 25G. Now, from the start there to the 25G is going to be 3 meters because it's uniform, so it acts in the center. And so this is also 3 meters on that side as well. Now, it's resting on rough horizontal ground, meaning there is friction. And also, because it's on the ground, there's going to be a normal reaction force. So that's the ground pushing upwards on the ladder. So we'll call that R. And then the frictional force, let's label that as well. We can call that F. Down there. And we know mu is also 0.25, so I'll put that information down there too. Okay, good. This is great. Next thing, it's now leaning against a wall. The wall is smooth though, so there's no friction there. But still, the wall is going to be pushing against the ladder. There's going to be some reaction force over there as well. So we've got to put that in. So I'll draw it in there, but we've got to label it as something else. So we can't call it R, we're going to call it... We'll call it P for now. There we go. Let's call it that. And then we've got this man. That's the last part. So the man now, who's climbing up the ladder, and he's 75 kilograms. And what we need to do is put him somewhere so that the ladder is, about to slip. So I reckon he's going to get, quite close to the top. So I'm just going to say the man's going to be around here somewhere. And then let's put that downwards as 75G because that's his weight. So we'll say the man is there. Do we know how far up the ladder he is? No. So what we should do is maybe call that distance X. Get that there. And we can say that's X meters. Perfect. One more thing is the angles. We need to get some angles in here because we don't have any at the moment. So we're told that it's inclined at 60 degrees to the horizontal. So let's maybe get this in here as 60 degrees. And then there's going to be a bunch of other 60 degrees that we can fill in. So here it is, right? So the first 60 degrees we can fit in is this one over here. And then another one over there. That's going to be 60 degrees too. And then what we'll do is create that there, nice little perpendicular down the bottom. And then this is going to be 60 degrees as well. Okay, perfect. And now because of Z angles, so there's a Z there, as you can see there. The angle at the top here is going to be 60 degrees too. So there it is. There's a diagram. We've got all the info we need. We've got loads of angles. We've got lengths. We've got all of our forces. We're perfect. We're all set up to do this question. So how do we do it? Now with ladders, there's a certain way you should always go about it. The first thing we should always do is upwards forces is equals to downwards forces. So set that up first. So anything upwards is equal to all the forces downwards. Now looking at our diagram, the only force acting vertically upwards here is going to be R. So we can say R is equal to, and downwards we've got the 25G and the 75G. We can add those together, right? So we can just say 25G plus 75G. And so what we've got is R is equal to 100G. Perfect. That's probably going to be useful. We'll keep it there for now. Now, step number 2 is then resolve in the horizontal direction. So forces to the left is equal to forces to the right. So forces to the left to begin with, we're going to have P, right? So P is the only force there acting towards the left. So we can say P is equal to, and the only force acting to the right there is going to be F. So we'll say equals F. So you've got that too. That's perfect. Now, we'll need to start taking moments in a second. That's going to be step number 3. But just before we get there, we know that what we've got to find out is where the man can stand so that it's going to start to slip. Now, what that means is when it starts to slip, that we're going to be in limiting equilibrium. Okay, so that's very important. When it starts to slip, we're in limiting equilibrium. And what do we know when we're at limiting equilibrium? Equilibrium, let's spell that correctly. Goodness. Right, when we're in limiting equilibrium, we know that F is equal to mu R. So that's F max. So we've reached maximum friction, and that's mu times by R. So what we can do is, well, we can substitute this F here for mu R. So we can say P is equal to mu times by R. And now we've actually got what mu is down here, 0.25. And we've got what R is, because you worked that out as well. That was 100 G. So we can say P is equal to 0.25 multiplied by 100 G. And so P is therefore going to equal 25G. So you've worked out what P is as well. So this is great news. Now, we've got lots of info. Last thing we need to do is obviously get an equation set up so that we've got X in there. Because at the end of the day, that's what we're trying to find. We're trying to find what distance this man can stand at. And so to do that, what we're going to do is take moments. And I'm going to take moments about this point here. Let's call this A, because obviously the ladder there was AB. So we'll say the bottom part is A and this part is B. So I'm going to take moments about A. So moments about A. And so if we're looking at our moments about A, because this is the point that we're taking moments about, we don't need to consider R and we don't need to consider F. Why is that? Because, well, they're acting at that very point. So there's no perpendicular distance to them, right? The distance is 0. So we don't need to worry about that. Let's highlight the forces that we do need to consider. So we need to go along here and we'll need to consider the 25G. We'll need to consider the 75G. And we'll need to consider the force P over here as well. Now what I'm going to do is I'm quickly going to put in perpendicular here. Now, the reason I'm doing that is because remember, to work out a moment you need to do the force times the perpendicular distance. Now from here what we could do is we've got distances to these forces, but then what we can do is resolve this force to the perpendicular. Okay, so likewise, even with the 75G, resolve that to the perpendicular, and then P as well, resolve that to the perpendicular as well. So that's the way I'm going to do this. So we'll start with in the clockwise direction, which is going to be the 25G and the 75G. So first of all, the distance, that's going to be 3 meters times by, and now we need to resolve this 25G, bring it to the perpendicular there. So that's going to be 25G cos 60. Now we need to consider the 75G. The distance there is going to be X. So that's X multiplied by 75G. And again, we'll have to cos 60 over there. And that's equal to, well, the distance to P now, which is right at the end of the ladder. So that's going to be 6 meters multiplied by. And then P, we'll need to bring that to the perpendicular. That's going to be P sine 60. Now let's maybe start to neaten this up a little bit. So 3 times 25G, that's 75G cos 60, plus we'll go 75GX cos 60 equals. Now we know P we actually worked out over here, didn't we? And that was 25G. So we've got 6 lots of 25G, so that's going to be 150G sine 60. There we go. Now let's start to work this around. So we can say 75GX cos 60 is equal to, I'm going to take the 75G cos 60 across to the other side. So 150G sine 60 subtract 75G cos 60. And then finally, to get X, what do we need to do? Well, all of this minus 75 cos 60, all divided by 75g cos 60. There we go, that's going to give us what x is. So let's quickly calculate this. So 150 times 9.8 sine 60, take away, we've got 75 times 9.8 times cos 60, all over 75 times 9.8 times cos 60. And we've got x as, we've got 3 sig figs, we've got 2.46 meters. Okay, there we go. And I think that should be that. Awesome. So, ladder question number 1 completed. So, important things to remember would be those 3 steps, right? First thing is you want to check your forces in the vertical direction. So, upwards equals downwards. Always start by laying that out. Step number 2, you go left is equal to right. So, set that equation up as well. And the last thing is take moments about somewhere. That's always step number 3. So, there it is. 3 very, very important points. And always set up a good diagram. Diagrams, lengths, all your forces on there, because that at the end of the day is going to help you see whatever you need to solve your problem. So there it is. Oh, and if the ladder is about to slip, then it's a limiting equilibrium. F is equal to F max. So do remember that too. Okay, perfect. More ladder questions coming. Stay tuned, and I'll catch you in another one of those videos real soon.